Okay. Right. So yeah, last term we did 10-dimensional case. So in 10 dimensions, we basically had you can kind of see on this part. But I won't write it much. I'll try and write over there. So last term we had 10-dimensional models where along with the space-time bosons, we had the space-time fermions, and then we had anti-holomorphic fields, which I think I called phi A, 1, 2. So if they were complex, we said these went from 1 to 16. And yeah, and that was just accompanied by the space-time bosons. But here I wrote this with a bar because it was anti-holomorphic, and this with a Z, it's holomorphic. So now we want to talk about what happens if we then go to 4 dimensions. So if we go to 4 dimensions, a bit more light on the board will help. Is that probably worse, Fareed? Or better? I think it's worse, isn't it? Yeah, okay. So then, yeah, going to 4 dimensions. So here, so this is, so in 10 dimensions, this index mu, we were talking in the light cone gauge. We could formulate the theory in the light cone gauge where the anti-holomorphic and holomorphic fields separate, and you can just take like wave equations in the transverse mode. So mu is from 1 to 8. So in 4D we should have something in where mu. So I'll write it here. So 4D we expect there to be 2 transverse directions. So if we're in the light cone gauge again, we could just say mu is from 1 to 2. So so we start off, and again we're going to have the space-time fermion mu, but this time the mu is just 1 and 2. So there's just 2 components, and then similarly we'll have x mu, the space-time boson, but that will be from 1 to 2, just 1 and 2 now as well. But the thing is that, you know, if you remember when we talked about these fields here, we had to cancel. The key thing was that we had to cancel the conformal anomaly. So that was like why we needed these 16 components here, because the 16 gauge fields created a C equals 16 conformal algebra, and then so in 10 dimensions you have sine mu and x mu, and they together these actually generate I think a C equals 15 superconformal algebra. But the point is that in 4 dimensions, you've only got 2 transverse modes, so two transverse directions, and the space-time part. So these space-time fields only create a C equals 6. So the 15 is like 10 from the bosons and 5 from the fermions, because fermions contribute a half, and then C equals 6 is 4 plus 2, basically, like 4 from the bosons, 2 from the fermions, because like, yeah, the conformal charge is half for a fermion and then 1 for a boson. So on the on the holomorphic side and the anti-holomorphic side, the conformal anomaly is not going to cancel now, because you only have a smaller contribution on both sides. So what we could say, this is the holomorphic part of the boson. So this is the holomorphic part of the boson, and then on the anti-holomorphic side, again in 10 dimensions, you had a contribution of 10 to the conformal anomaly from this, but so this would be like C bar equals 10 in D equals 10, but in 4 dimensions you've only got C bar equals 4. So again, you've got an extra 6. So we need an additional 6 contribution to C bar, and we need an additional 9 contribution to C in order to cancel the conformal anomaly. Tilt like this. Okay. Yeah, so we have to basically introduce extra fields that cancel that conformal anomaly. So if we're going to choose fermions, and the fermions contribute a half, so we have to add. So if we want to add C equals 9, so to get, if we've gone down from 15 to 6, so we need to add 9. So that could be done with 18 fermions. Yeah, so half times 9. Half times 18. So that would be on the holomorphic side for C. And then if we want to add 6 to here, to C bar, we need 12 fermions, 12 real Majorana fermions. The contribute C equals a half. Does that make sense? So like, basically what we've got now, so what we've got now in 4D, so write it here. So in 4D, we've got holomorphic fields, psi mu, and mu is 1, 2. Then we need basically 18. So what I'll say is, well, I can just write the notation that we usually use. So we need 18 fermions. So we write these as chi, y, and w. And these are, so chi 1 to 6, y 1 to 6, and w 1 to 6. And so this contributes C equals 9 to the holomorphic side, and then this along with x mu, so this would be like C equals 2, and then the x mu is C equals 4, and overall that cancels because we get C equals 15, which is what we want for a superconformal algebra with no anomaly. So that's on the holomorphic side. So then on the anti-holomorphic side, you've still got the gauge, like these 5 bars. So we still got 5 bar, 1 to 16. Okay, but then we have to introduce. So these are all, by the way, real. So these are real fermions. And so this is C equals 16. The x mu bar contributes C equals 4. So we still need, I mean, we need C equals 26, like the bosonic string, right? Remember the heterotic string is like one side, it's basically the bosonic string, so it has 16 conformal dimension 16, sorry, 26. And in 10 dimensions, that's sort of easy because you just add on these, you just have 16 components. But in 4 dimensions, you have to add in an extra 6. So it's like, you can think of it as like the 6 compact dimensions, like between 4 and 10. So you have y bar 1 to 6 and w bar 1 to 6. Okay, so that's the fields you need to cancel. They're all the anti-holomorphic, these are all the holomorphic. Okay. So what we've done is, by going to 4 dimensions, we've just basically had to introduce 18 real fermions here on the holomorphic side, and 12. So these are going to be a C equals 6 contribution to C bar, so C bar equals 6. Okay. And what we have is all the rules that we did in 10 dimensions, like the GSO phase rules, modular invariants, are all going to be very similar, but we just have these extra fields in 4 dimensions. So the Y's, the W's, and the chi, and the Y bar, and the W bars. So we'll get used to using these extra fields, but basically all the rules are the same. So maybe what I can do is rewrite that a little bit. So, for example, when we, you remember from last term that whenever we build a free fermionic model, we always start with a Ramond sector, which is given by the 1 basis vector. So the 1 basis vector, remember, was the basis vector in which all of the fermions are periodic. So it's like a Ramond sector for the theory. And in 4 dimensions, you know, we would write it like so. So psi mu, we've got the chi's, we've got the w's, and the y's and the w's, and then y bars, w bar, and the complex fermions, phi bar, that runs to 16. Okay. So all of our models are still going to start with 1, this basis vector, but now we just remember that there's these extra fields that make it a 4-dimensional model. So you can see it's a bit more complicated than 10D, which is why we started in 10D. It's simpler because there's fewer fields. Right. So if you remember, so remember this side of the theory is a superconformal field theory, or superconformal, let's say superconformal algebra, SCA, with C equals 15. But it should be supersymmetric. So it should be supersymmetric. So Worldsheet Susie. So it's always really important to distinguish worldsheet supersymmetry from space-time supersymmetry. When we were talking last term, we talked a lot about, like, when we did the spectrum of models, we looked for the Gravitino. And then we looked if there was a gravitino in 10 dimensions, we found supersymmetry, space-time supersymmetry. So that's when you look, when we had this S sector in 10-dimensional model, we had this S sector that gave us a gravitino, basically. We got n equals 1 because we had one gravitino, right? So that was space-time supersymmetry. So the theory, if you remember, we did first a model with just the basis vector 1, which didn't have a gravitino, but then we introduced S and we got a gravitino, which was like n equals 1 supersymmetric model. But there was also worldsheet supersymmetry, which is the symmetry essentially between having like psi mu and x mu. And in the worldsheet theory, there should be basically in order to have a super conformal algebra, you need a symmetry between the psi mu and the x mu. And in order for that to be the case, you need what's called a supercurrent. So we need a supercurrent. So supercurrent is like, it's just like Noether's theorem. You get a conserved current when you have a symmetry. So if you have supersymmetry, the supercurrent is the corresponding conserved current. And in 10D, worldsheet supersymmetry is given by this. So let's call it TF, and we'll call it TF10 because it's 10D. Okay, TF10 is like the sum of like psi, or we just wrote psi mu, and then the like derivative operator on x mu. And this is in the, if if we're doing the light cone gauge, again, we just had mu from 1 to 8. And then there might be, I think there's a factor of I, probably. Should be a factor of I think. But basically, this field will exist. This is a conformal field of conformal wave 3/2, which is like a worldsheet. It's a bit like a worldsheet gravitino generator. But you remember, this is kind of like we almost expect to have a derivative of the bosonic field because this is a conform. If you remember, I said, I don't know if I didn't really prove it last term, but x mu on its own is not a conformal field. You have to take the derivative of x to get a conformal field. So your psi is a conformal field, you multiply it by another one, and then you get this 3/2 because this is like c equals half, this is like c equals 1. Combine them, you get c equals 3/2. And this field will make sure that your algebra is super conformal, has supersymmetry on the worldsheet, okay? But in 4 dimensions, so I don't know why I wrote this, so let me just rewrite this in a normal way. Okay. And then in 4 dimensions, well, so then in 4 dimensions, you have to kind of extend this, and I'm just going to tell you what happens. But basically, in order to get worldsheet supersymmetry, you have to ensure that there's the following. So, okay, maybe what I said, let me just rephrase what I said here. So, in order for the theory to be worldsheet supersymmetric, like this supercurrent has to be preserved. So if you introduce new basis vectors that change this object, which we'll kind of understand more in 4 dimensions. But if you could introduce a basis vector that made this not be preserved, like multiplied it by like a minus sign in a way that stopped it being preserved, then you would break Worldsheet supersymmetry, would be bad because it sort of makes the theory inconsistent. And we'll see this and what this means in 4 dimensions in a second. Okay. So that's what I mean. Like you could obviously write down this operator, but if you add in basis vectors, you're changing the theory, and potentially you could you could make this not invariant essentially. And then if it's not invariant, then Worldsheet supersymmetry is broken. So we'll see examples in 4 dimensions. So in 4 dimensions, this looks similar because the first term is similar. It's this sine mu d. So now you've got the sum, but the sum is only from mu equals 1 to 2. Okay, in 4 dimensions, so from 1 to 2. And then you've got sine mu dx mu. Okay. And then you also have, so basically what happens is that these fields, so remember we're looking at this side of the theory where you've got supersymmetry. You've also got the chi, the y, and the w. And so they actually come into that, they can affect the supercurrent. So the form that it takes is quite simple. I think there's an I again, and then sum over basically chi, y, w, multiplied together. So this would be like from, let's say, capital I equals 1 to 6. So you're sort of summing over all of the chi's, y's, and w's like this. Can you see that all right, Farid? So this is an important equation. So to make sure you get this clearly. Okay, so it's the same. So you've got this same thing as you had in 10 dimensions, but now added with this kind of triplet of chi, y. Yeah, there should be an I here, I think. I can double check from my notes maybe, but the I just yeah, it's with an I. I'm a bit lazy with some of these details like that, but okay. So this again, this is important because basically in 10 dimensions, preserving this is quite trivial, but in 4 dimensions, because there's this chi, y, and w. Basically, what this means is if you add basis vectors into a model, this has to be invariant. And so, like, if you add a basis vector, that basis vector will give a boundary condition to chi, y, w, and psi, right? So basis vector, like, so here 1 gives boundary condition 1, 1, 1, 1. And that's fine because it's invariant in the sense that if you add a 1 here, by giving this boundary condition 1, really there would be like there would be a minus sign essentially. So no, sorry. So this would basically get a minus sign, and then here you get a minus sign, minus sign, minus sign. But overall, this minus sign will cancel this minus sign. So I'll write this in a clearer way. But that's the idea, is that the boundary conditions you give to these have to basically compensate the boundary condition that you give to the psi mu. And I'll write this as a clearer equation. So preserving Worldsheet supersymmetry. So preserving Worldsheet supersymmetry is equivalent to preserving TF4 And preserving TF4 would be that basically for all, so I'll write it here before I write the equation. So basically saying that for all vectors in our basis, so for all like vi in B, so all of our basis vectors, that the boundary condition, so I'll write the boundary condition as like alpha. So maybe actually, yeah, maybe I can write this as like for all alpha. I mean, alpha, if you remember, is what I generally use for like a sector, like a linear combination of basis vectors. So, I mean, if you preserve it for the basis vectors, you will preserve it for the whole vector space. So it's equivalent to writing for all vectors in the basis, but you could also write for all sectors in the whole vector space. It doesn't matter. It's just just a choice. And then if I write alpha for the sector, I'll write alpha without an underline for the boundary condition of a fermion in alpha the vector. So alpha to the boundary condition of psi mu in alpha. I'm not going to have enough space here. Plus, I'll write this again. So the boundary condition of psi mu plus alpha of chi I plus alpha of yi plus alpha of wi is should be even. Okay. So you could write actually wait, let me just fix this. Okay. Yeah, so actually it's better, sorry, right, so psi mu, the boundary condition of psi mu could be, yeah, let's say the boundary condition here should be compensated by the boundary condition here. So you say this boundary condition is equal to this mod 2. Mod 2. Okay. So this is a very important rule. So all basis vectors should preserve this this in order to preserve worldsheet supersymmetry. So for example, if you had a basis vector, maybe I'll give an example where this isn't true. So so notice that remember I is from 1 to 6. So I is from 1 to 6. So this is really like 6 equations, really. Because you have to check it for I equals 1, you have to check it for I equals 2, and so on. So just as an example of a basis vector where this isn't true, you might say, let's say V is equal to psi mu. And then if I put, let's say, chi1, chi2, and then chi3, chi4, chi5, chi6, I'm just going to say they're anti-periodic, so they're 0. So I won't write them. Remember, when we write the fermion, that means that it's periodic, or it's Ramond. So these 3 are Ramond. But then this one and this one, so at the moment, chi1 and chi2, I could, if I wrote, so at the moment, I equals 1, so I equals 1, you'd say, okay, this is 1, and this is 1, and these are 0. So that's fine, it's preserved, because 1 equals 1, it's fine. But chi3, chi4, chi5, and 6. So let's just end this. Let's just end this there. Okay. So this would violate the supercurrent condition because so for I equals 3, 4, 5, and 6, right? Psi of mu is obviously equal to 1. because it's in the vector, and then is equal to so does not equal alpha chi I plus alpha yi plus alpha wi, because this is 0, this is 0, and this is 0. So it's 1 equals 0, which is not true. Okay? You could also violate it. For example, similarly, let's say in the vector I put, well, what if I put y 3, 4, 5, 6? Okay. So at the moment, if I put y 3, 4, 5, 6, this would basically make this 1. Like if I ended it here, then this would become 1 for I equals 3, 4, 5, 6. And then 1 equals 1, so this is preserved. So this would be 1 because I've put it in the basis vector now. I've said these are periodic now. I've changed the basis vector. So this becomes 1. I'm just making this up, just like that. Yeah, so I is 3, 4, 5, and 6 in this case. So then we've still got psi mu is 1. Then I've added these in, so this is 1, so it's 1 equals 1, so that's preserved. So this one is fine, yeah? So that would be equal. But now let's say I put in, if I change the basis vector again, you know, I could put in y 3, 4, 5, and 6 as well, okay? And this would then be, well, this is 1 still, but then all of these w's are 1, yeah? So then it would be 1 is equal to 2, or 2 mod 2, which is 0, but either way, it's not true. So 2 mod 2 is 0, right? So this would then be not true. So this choice does not preserve the supercurrent. Do you get the idea now? It's like you just have to check psi mu, and then these 3 boundary conditions for each I from 1 to 6. Is that right, Fareed? Make sense? Okay, cool. Right, so that's a kind of a condition that we have to think about more in 4 dimensions than we did before. Because in 10 dimensions it's kind of trivial. Because in 10 dimensions we didn't have this chi, y, and w part, so it didn't really. We just had to match up the boundary conditions with psi, so it's fine. Right, so what's next? Okay, so what we should probably say is that I kind of skipped over a detail, which I'll try and explain somewhat simply and not spend too much time on. But so the supercurrent that we wrote down could be, we could have written it slightly more generally. So in general, this supercurrent, so I sort of well, let's just write it by mu. Okay. And then plus I. We could have introduced, there are a couple of ways to put, you could put a number here, like some kind of numbers here, which still make this supercurrent consistent. So so chi I wi. Sum over I from 1 to 6. So these, there are actually 3 choices. And let me just check. So in 4 dimensions, there are actually 3 choices here. And F, A, B, C. Yeah, maybe it doesn't, yeah, maybe there's some details here. But so there's really, yeah, in 4 dimensions, there's 3 choices. F, A, B, C can be structure constants. The structure constants, remember, is like when you have a Lie algebra and you take commutators, and the structure constants are like what appears on the what the commutator is equal to. So there's a structure constant, and then so like yeah, if you had SU2, you'd have like the commutator of the generators of SU2, and then structure constants of SU2 times the other generator. So the structure constants are, sometimes you can just think of it as like a way of defining a group, and defining a representation of the group. So the structure constants, so they can be the structure constants of 3 groups. So these 3 groups are basically are the 3 groups that would allow you to define a consistent supercurrent. So those 3 groups are SU2 to the 6, and then SO5 cross SU3. And really, these are groups. So these groups would basically relate to these chi's, chi, y, and w. So it's basically like telling you these groups tell you like what group these transform under. Okay, so a bit like when we talked about the gauge sector transforming under a gauge group. There are 3 choices on how these can transform in order to have a consistent supercurrent. This is really a technicality that's not that important, because we're gonna, in a second, I'm just going to tell you that we always choose this group. But I'm just mentioning it because it's just something that's really just in the background. But so what this is saying is like, so SU2 to the 6, this is the choice essentially where every like triplet I, Y, and I is just transforming in the same way. So each one is transforming as SU2. And in particular, like a representation, like a triplet representation of SU2 is actually like the adjoint. So it's like the natural matrix representation. So this is, these transform as, so transform, so for F, this is, so this is, yeah, for FU2 to the 6, this is that each of these 6, so these 6 triplets are basically adjoint generators or transform, transform as or under the adjoint of SU2. Okay. And this is the choice that we'll take. And what this means for us is there anything else I want to say about that? Not really. So this I mean, this is a bit like, yeah, it doesn't matter about the group theory details here because I don't want to get distracted for now. But the point is that we take SU2, and actually SU2 had or sort of was proven, or I'll just say can be proven to be only choice that can give space-time smoothing. Okay. If you take these two choices of the group, then essentially what these two, because these are two different groups and these are two different groups, you're essentially making the 6 sets of chi, y, and w. They're going to be transforming like in different ways. Like maybe this would be like, you know, the first this would be like the first, like, so for example, this one would be like the first 2 transforming together, and then this would be like the next 4 transforming together, something like that. And when we want to have space-time supersymmetry, you know, you want to get a gravitino, and basically giving these different different transformations or different groups for these chi's, particularly the chi's, because that's what's going to come into the gravitino, is going to essentially throw off any worldsheet, any space-time supersymmetry, and it's only this one that can give you space-time supersymmetry. So we choose this, and for this case, so for SU2 to the 6, this is just these structure constants are, so what the structure constants are for the adjoint representation. So the adjoint representation is like the simplest representation of a group. It's actually the representation where this is just one. Yes, yeah. If we use SU2 to the 6, we're taking these to transform under the adjoint. And for the adjoint representation, the structure constants are 1. Okay. So that's why I wrote the supercurrent without this detail about the structure constants before. So I could have just skipped that detail, but I wanted to include it just because it's technically important, but practically not important. Okay. So all you need to know is, that these chi, y, and w's as triplets, they should transform together. Okay, sorry about that. But it's just something to, maybe if you want to know more about it, I can give you references, but I'm kind of just giving the results of this. Right, so, but in general, we just write the supercurrent like this. Right, so what else to say in 4 dimensions? So we could start, so what's the time? So it's fairly late. So we could start doing like a model. You think if there's anything else to say? Let me think. Okay. Maybe I'll just make some comments about the structure of the models rather than starting doing a model. Maybe we'll start doing a model next week. So next week we can start doing the like 1S model. E6. What are you asking for, Reed? Which group would it be in this case? E6. Okay. Structure constants. Yeah. Yeah. So off the top of my head, off the top of my head, I don't know what the structure constants would be for the other two groups I wrote, the SO5 cross SE3, SE2 cross SE4. I have to think about it. But yeah, okay. Anyway, so yeah, a couple of notes about the model as well is actually because of this SE2 grouping, we will generally complexify. So we will complexify the chi's such that chi, so we will always write the chi's as complex like this. So chi1, 2 is like, the normal thing we do when we complexify. We take something like the sum of the real parts and then normalize it. Okay. And similarly for chi 3, 4 and chi 5, 6. So the chi1, so chi1 and chi2, we just can group them together, like using this complexification. Same with chi 3, 4. So there's really only 3. So instead of having 6 real fermions, we have 3 complex fermions. So now, basically, the only real fermions are the set YW and YW bar. Okay. So all the others will be complex now because psi mu is complex, chi 1, 2, chi 3, 4, chi 5, 6 are complex. And on the anti-holomorphic side, we have phi bar, which is complex. We generally will write phi bar as 16 complex fermions. So these are the only real ones. So this is from, so we could write I with 1 to 6. So we have 12 real fermions on both sides. Okay, so that's just some comments. Then I'll make a comment about these. So these Y's and W's are important. So so what I've presented so far is really, well, we're really thinking of string theory like a conformal field theory. All we talked about was the cancellation of the conformal anomaly. But usually in string theory, you have this idea of having like a theory in 10 dimensions, then going down to 4 dimensions, you have 6 dimensions, which are like compact, like in compactification, it's usually how other people in string theory talk about it. So you have some 6D manifold or some space that's compact in the sense that all the directions like close upon each other, and we might want to make a connection between that idea of string theory as as a 10-dimensional theory that's compactified to 4D. And this theory, where we basically just formulated a conformal field theory which matches the conformal sort of dimension of the string, the superstring, the heterotic string at least, and make sure that the conformal anomaly cancels. But at the moment, there's no geometric picture, like there's no manifold, no 6-dimensional manifold or anything. So the way that we do that is these y and w's from 1 to 6, they're going to relate, we will relate these to a 6-dimensional compact internal space. So these will be like, so this, remember, is 12 fermionic coordinates. You know, if it's a 6-dimensional internal space, you'd imagine that it would be defined by like 6 normal coordinates, like 6 bosonic coordinates. So to sort of maybe make the connection more obvious is like you'd have to bosonize the theory. So this would be like saying, so sort of like normal geometric coordinates would be bosonic, so we'd have to bosonize. So bosonizing back, because we're in the free fermionic, we are, all of our fields are fermions, but if you wanted to go back to a geometric picture, which would be a bit like, well, which you can think of as like if you just look up orbifolds, orbifolds start off with bosonic coordinates and then do the same stuff we're doing, but with bosonic fields, basically. So we could basically go back to the bosonic language by taking 2 of our, if we take 2 of the holomorphic y's and w's, so yi and wi, so we could take y1 and w1, then we could bosonize these by saying, well, at the level of conformal field theory, 2 fermionic coordinates can be basically give the same operator product expansions and contributions to the conformal algebra and so on as the derivative of a bosonic field. Okay, so we can actually get 6 bosonic fields on each side through this bosonization. And then you could, that's the sort of how you would start off making the connection between what we're doing, this sort of worldsheet conformal field theory perspective, and a more geometric picture of a 6-dimensional space where the coordinates are xi, and the sort of, this equation is like a way to make a connection between the two. You could also make the connection, so this is actually equivalent in the end to yi plus iw. So like if you it's like complexifying these two as well, you could say is equal to because of the conformal rules of conformal field theory, complexifying these two, you'd actually have to take an exponential of the bosonic field. Might be some parameter here in general, but yeah, there might be some alpha here or some parameter, but it doesn't really matter. Okay, so this bosonization, you can either in general think of bosonization in terms of this, like relating this product to this derivative of the bosonic field. Or you can think of it as like, if you complexify the fermions, this complex fermion would give the same like operator product expansions, contribution to the conformal algebra as this exponential of a bosonic field. Okay, and we're not doing this like, we're not going to be doing like the details of this. I'm just making the connection for you. So maybe we can revisit the connection in more detail later. But this is how you would relate like the usual like orbifold language, which is geometric in nature. Talks about a 6-dimensional internal space with coordinates, like normal sort of coordinates like x, I, and yeah, you would make the connection through this bosonisation basically. And then there are some details here that are, yeah, lots of details here that I'm missing out, but I think we will come back to this in a few weeks, but yeah, this is it. Okay. Okay, I think that's enough for this week, and then next week we'll do a couple of models in 4 dimensions, and then see that we're basically applying the same rules, like these GSO rules, and doing the GSO projection it's all the same stuff, but it's just with these slightly different more fields in 4 dimensions. Okay, I'll see you. We'll try and do next week. Is next week good for you?